Okay, good afternoon, everyone. Sorry, good morning, everyone. As you can see, I'm already ready to start the weekend. Need to get caught up on a lot of grading work and other pending work. Okay, let's see. Let's pick up. Page 17. There we go. All right. E201, we're on lecture 4 in homework 3, 4, 5. All right, so homework 3, 4, 5. I think homework 3 was KCL, and 3 and 4 were KCL and KVL. So questions regarding those homework. Any questions about concepts, application of the laws, as well as any specific problems? How many of you are done with homework 3? Okay, pretty much everyone. Homework 4? You? All right, 5. So, okay. Any questions regarding homework 3? Going once, going twice. Okay, gone. How about homework 4? Questions regarding homework 4? Okay. All right. How about homework 5? Questions regarding homework 5. How many of you have already attempted homework 5? Okay. Comfortable with homework 5? Circuits and elements. If you have not yet looked at it, how many of you would like to take a look at it right now? Okay, 1, 2, 3. Okay. All right, let's do that. Introduction to circuit elements. We have 4. Let me change screen sharing. Okay, for those of you who are online, can you hear me correct? Hear me all right? And can you see homework 5? Okay. All right, thumbs up, thank you. All right, so this is about circuit elements and fundamentals. In some ways, this can also be homework 1 because we're talking about like the basic introduction. So correct definition of a conductor, correct definition of an ideal voltage source, ideal current source. These are like the most basics, questions about the most basics, most fundamentals. All right, so in one of the slides in the notes, I have I talk about nodes in an electrical circuit, nodes, electrical loops, electrical meshes, and a branch. Okay, so we have nodes, branch, mesh, and a loop. Okay, so anytime we have two or more components coming together in any electrical circuit diagram, that is known as a node. So a node in an electric circuit is simply the junction point between two or more elements. Intersection, junction. Okay, junction or intersection, whatever we want to call it. Okay, so node again is any point in a circuit where two or more components come together. Now, if you have a circuit diagram, let's say you have a element like this, element A and element B, and perhaps you have element C. Some circuit diagrams or some engineers would like to draw a circuit like this. More often than not, you would see a dot at that junction point. And when you see a dot it's quite obvious that it's a junction point, it's a meeting point, and so our brains automatically think that that is a connection. So that's a node. However, if there are only two elements, let's say something like this, A, B, C, and D. We talked about this a little bit last class, right? So the node between C and D is not explicitly marked, yet it is still a node. Okay, so that is a node. Basically a junction point or a meeting point, whether it's explicitly marked or not. Then if there is a, let's see, how do I want to draw this? If there's an angle in there, that is still a node. Okay, it's not two nodes, it's just one single node. And I believe we talked a little bit about this also. Now, if you have two nodes in a circuit, anything that is connected between those nodes is known as a branch. So between these two nodes, this is known as a branch. So it's one branch of a circuit. So anything between any two nodes in a circuit is referred to as a branch. If you see something like this, and perhaps there are other elements connected to the right of the circuit, it doesn't matter. As long as there is a wire between those two nodes, it is still the exact same node. And so I would mark this. One node. Okay. So going back to the homework question, what is defined as a conductor? Well, as the name suggests, a conductor is something that allows electrons to flow through. It allows the conduction of electrons, which in this case would be any kind of ideal wire. So ideal conductor is basically a wire that connects two junction points in a circuit. Now, if it's the exact same node, sorry, if it's connected by a wire, that means it's the exact same node, right? And if you have two nodes connected by a wire and you try to measure the voltage across those 2 points, what is the difference in electrical potential between those 2 points? Remember the example of an extension cord? If it's 120 volts at the power outlet and you have a 100-foot long or 100 feet long extension cable, 100 feet away, you still have 120 volts. So what is the difference between those two ends? It's 120 here, it's 120 here. What is the difference? It's zero, right? So it's zero. So look at the 4 choices. What do you think? A, first one. So the voltage across a ideal conductor will always be zero, no matter what current is flowing through it. And the keyword is ideal. Again, remember, all of electric circuit theory that we learn here is theoretical, meaning everything is ideal. All components are ideal. They are not affected by any real life conditions. Okay, so correct definition of a conductor or an ideal conductor. So the voltage would be equal to 0. And the resistance of that conductor would also be equal to 0. That's not explicitly stated here, but an ideal conductor, which of course does not exist in real life, has a resistance that is equal to 0. Hence, in a circuit diagram, if we have a small dot, small dash, small line, or a long line, they're all exactly the same. We treat everything exactly the same. The resistance for all of those is 0. So an ideal conductor will have resistance R equal to 0, and the voltage across the two ends of the conductor will also be equal to 0. All right, any questions? Sorry. All good? Okay. Correct definition of an ideal voltage source. We talked about this in class or not? Not yet. So I'm teaching like 4 different classes and there are some overlap. So I have to keep track of what I talked about in what class. There's a slide and there's a lecture video where I talk about dependent and independent sources. And the sources are of 2 kinds. We have voltage sources and we have current sources. Okay. In real life, there is no difference between the two. If a source is supplying voltage, there is current that accompanies it. If a source is supplying current, there is voltage that accompanies it. Okay. So if we look behind us, there are lab benches, and each one of those lab benches has a DC power supply. That DC power supply can operate both as a voltage source and as well as a current source. The only difference is that to operate as a voltage source, it will keep the output voltage constant. And it would change the current to match the requirement of the load. If it's a current source, it will keep the output current constant, but it would change the voltage to match the requirement of the load. So let's look at an example. What? Oh, this got pulled out. Okay, let's go to our notebook. Where did that go? Okay. So let's say we have a source. The source is rated to supply 10 volts between its output terminals. You're all familiar with Ohm's law, V equals IR. What happens if we connect a resistor of, let's say, 100 ohms? What is I? You don't have to draw this out, just simply for explanation purposes. V is 10, R is 100, V equals IR. So what is my I? Anyone? Feel free to speak up. There's no penalty for speaking up. 0.1 amps, right? So voltage source is going to supply 10 volts, 100 ohm resistance. Current is 0.1. What happens if we change the load to 10 ohms? What is my I? 1 amp. So what is happening now? The load's requirement has changed. Load is now 10 ohms, but the voltage source is rated to supply 10 volts. So it will supply 10 volts, but it changes or adjusts the output current to match the load's requirement. If you change it to 1 ohm, current is now 10 amps. Right? Again, it is keeping the voltage constant because that is the property of a voltage source. It keeps the voltage constant. It changes the current depending on the requirement of the load. Does that make sense to everyone? Let's take a pause, think over that. Let me know if you have any questions. Okay. Any questions? And the same thing happens when it's a current source. So let's say you have a current source, and that current source is rated to supply, let's say 10 amps, just for the sake of it. And now you have a resistor that is, let's say, 1 ohm. So what is my V? V equals IR, so 10 times 1. I get 10 volts across that load or across the output of the current source. If the resistance changes to 10 ohms, my V goes to 100 volts. If it changes to 100 ohms, V goes to 1,000 volts. So the point of this is that the current source will supply its rated quantity, meaning if it's set at 10 amps, it will supply 10 amps regardless of what is connected at its output terminals. It will change the voltage across itself at the output to match the requirement of the load. And that's what makes it a current source. That's it. There is no other difference or physical difference in the actual power supply. And so the mode of operation would be called as constant current, or CC. All right, let's take a pause, think over that. Let me know if you have any questions. If you're online, just feel free to speak up, interrupt and speak up. If you don't type anything in the chat. So if you type anything in the chat, I won't be able to monitor it. So how many of you are taking EE251, the lab class? Okay. Which rooms do you all remember? 130, 126, 127, 147. So let's see, 147 has Rigol power supplies, RIGOL, I believe. Beige, it's rectangle, but it's more closer towards a square front panel. At the top, you have three channels, right? Three individual power supplies in there. So at the top of the LCD screen, next time you're in the lab and you turn it on, take a look. There's a tiny notation which says CV. And when you turn it on, it should light up. CV should light up. Okay. If it exceeds its rating, it might drive it into current protection. It might go into constant current mode, and CC would light up. We don't want CC, we want CV because we're always working with constant voltage modes. So when CV lights up, right next to it, there will be another notation called CC. And of course, CC will not, will not be active. The next time you're in the lab, take a look at the front panel of the power supply, and you should see a CV in there and a CC in there. Okay. The power supplies that we have in the back have the same thing. I think it's the bottom. I can't remember on this one. These ones are new. But somewhere on the front panel, again, there is a LED indicator that says CC and CV. That's how we know whether it's a voltage source or a current source. All right, so let's get back to the questions. Circuit elements. So correct definition of an ideal voltage source. Hopefully you'll be able to answer that now. And the same thing with the correct definition of an ideal current source. Okay. Choose the correct statement of Ohm's law. That shouldn't be too much of an issue. And then here is the one that does cause issues. Draw a circuit that contains a 5 ohm resistance, a 10-volt independent source, and a 2-amp independent current source. So any questions about this problem? Have you all attempted this, first of all? So I'd like students to attempt this and then let me know if you have any questions. The purpose of these questions are to make the students think, have a process, and then come up with any questions that they may have. Yes. Okay, so a question being asked is how would we connect it in series if there is a, you're talking about this one or you're talking about this one? This one? This one, right? Oh, this one. Well, I think the question is designed, well, it's not designed. It's straightforward in a sense, but it's also very twisty in a sense. It's basically just asking students to recognize which is a series circuit and which is a parallel circuit. That's all it's asking. Yes. So we are given two options, right? Exactly. Yes. So as I said, in some ways the question is straightforward. In the other ways, it's very twisty because it provides us two options and it doesn't tell us. So I think part of the question is recognizing which diagram we have to use for the series circuit. That's what it is. It stumped me too the first time I looked at it. So, and if I don't teach 201 for like a couple of quarters, every time when I open it up, I'm still stumped. But then I remember. So there is a series circuit in there, and there is a parallel circuit in there, and so we just have to choose which one is correct, and that would be it. All right, let's see. Was there a different part to this? No. Okay. Any other questions about this one specifically? Okay. How about next? All right. Any questions about this one? Power is delivered to a resistor and the applied voltage is given. So it asks you to find the resistance and then also again asks you to find the power when the voltage is reduced. So for this, it would take you to here again. I'll show the equations that we would need, but students should of course attempt this on their own. So we have two equations, right? We have V equals IR, and then power is the product of voltage and current. So V equals IR and P equals VI or P equals IV. If you want to stay kind of consistent, we can do P equals IV. From these two equations, we can derive power in terms of the resistance. So we can write P equals V square divided by R, or power is I squared times R. Okay, these are the only equations you need. So if you know the value of the resistance and you know the voltage being applied or the current flowing through the resistance, you can directly calculate the power. You do not have to apply Ohm's law and calculate it that way. So we know power is given to us in that question. Voltage is given to us. We simply choose the equation and then calculate the third quantity. All right. So again, solve this and let me know if you have any questions. Done with that one? Any other questions? Anyone move ahead in the lecture videos? Meaning for this week, I had 4 lecture videos, I think. Monday, Tuesday, and Wednesday was the suggested, but students are free to move ahead. It's the same playlist. Say anyone move on to like video number 5, 6, or 7? I'll explain. So this is simply the guide. Okay, so week 1, I had like the introduction, 2, 3, and 4. And then I think this takes into resistive circuit analysis, and then actually 5, lecture 5. Okay. And then after that, you can actually just click on the same video and go to that same playlist if you want it. And let's see, no direct playlist. So spring 2024, which is this one. And so this obviously has everything. But lecture 5 onwards, we move into the new analysis techniques. And so I will go over the explanation in class again. In addition to the lecture video that I have, I will also go over it in class, right? That will be next week, not this week though. And then MCA is mesh current analysis, superposition, and Thevenin-Norton. It's again one of the most important topics. And that again is something we'll do in class. But if you don't just if you get done early and then you do wish to, you have some time on your hands, you wish to jump ahead, then the entire playlist is available. You can get started with the next topics. Okay. One final prompt about homework 5. Yes. Let's see. You mean the answer? Oh, we'd have to calculate. So question being asked is, how is the answer not 10%? First indication is that the power equation is not directly proportional to the voltage or the current. So P is directly proportional to the square of the voltage. So P is equal to electrical power is V square over R and I square times R. So not directly proportional. So if the voltage increases or decreases, the power will increase or decrease as squared of the voltage and current. So that's the first clue, right? So here, right? Square of the voltage and current. So the standard procedure to determine this homework, I'm sorry, not homework, this question would be, first we apply the equation P is equal to V square over R, and we can find the resistance from there. That's a 160, and then we have 100. So it would be 10,000 divided by 160. That would give us the resistance. And from there, resistance, of course, does not change. But now we change the voltage from 100 to 90 and plug it back into the same equation to calculate the power P. So it would be 90 square, 8100 divided by the resistance that we obtained in the first step. Did everybody get that? Uh-huh. Yeah. We would not be able to apply Ohm's law directly because we don't have, we have voltage, but we don't have resistance. So we won't be able to find current. And so in such cases, we use the direct equation of power. And if, you know, those alternative equations, which is V square over R and I square times R, they are derived from Ohm's law. All of these analysis techniques are tools. There are tools in our toolbox, and we can use them in any order we want in order to solve for a circuit. Okay. Let's say if you're working on a mechanical system and we have to, let's say, screw in or unscrew a bolt, we could use a pair of pliers to do the job, or we'd have a spanner, or we'd have a monkey wrench. All of those tools can do the exact same job, except one tool is more efficient and easier to use than another one. So it's the same case with circuit analysis techniques. We have multiple different techniques, and we could possibly solve a problem using 2 or more different techniques. We just need to figure out which one's the most efficient. So there's no right or wrong answer in that case. Okay, any other questions regarding this homework? I believe this is the last one, right? Okay. Okay. Let's move to homework 6. I think that's about combining resistors in series and parallel. Anybody take a crack at that yet? Homework 6. All right. So for the most part, I'm assuming students recall this information, like how to combine resistors in series and parallel. Yes, right. So let's talk about a little slightly different one. And I do have a technique that I show in one of the videos. Anybody taken, anybody start on homework 6 yet? Anyone? Okay, all right, great. You have any specific questions? Okay, all good. All right, so this is just given 5 ohm resistor in series with it. So you just have to draw out the circuit diagram. Equivalent resistance is already given to us. So we are actually solving for an unknown resistance that is part of the circuit. So we have to determine the value of that resistance. This is the one that students typically have some trouble with. Did you do all right on this one? Okay, great. And then see this one. This is another, it's kind of straightforward, but it's a little tricky. So I can go over this one too, and then this one. All right, so what I'm going to do is I'm going to use that technique and I will show how we can solve for this circuit. Okay, we are asked to find the total equivalent resistance between the terminals A and B. So how would you proceed? Well, there's a technique that I developed, and to the best of my knowledge, I have not come across that technique in any of the books or from anyone else, another person. Okay, so we have our measurement terminals. We are asked to find Req between these terminals, right? So let's just say Req between these terminals. Well, in this technique, what we're going to do is we are going to draw 2 horizontal lines in parallel that are spaced at a distance. I'm going to call A and B. And the objective is to draw every resistor vertically, starting from A and making our way towards terminal B. And so at the end, the objective is that all resistors are in parallel branches, and we can simply combine them either in series or parallel to find Req. This technique does work on most circuits. There are some circuits that are not reducible just because of the way the connections are. Okay, for those circuits, we can't find Req by any normal means. So, as I said, the objective is to draw out a resistors vertically going from A to B. All right, so let's begin. What is connected at A? We have if we start from here, we have 40 ohm resistance and a 30 ohm resistance, right? So I'm going to draw, let's say, start with 40. Okay, this is my 40 ohm resistance. And the objective, of course, is to reach B. So if I start with 40 ohm resistance, it's going to E, which is then going to B. So what else do you notice? Actually, maybe I should have started with this first. What do we notice about nodes E and B? What is connected between E and B? There's a wire. So there's a wire between 2 nodes. It means it's the exact same electrical node. So B is the same as E. And same is the case with A and D. A and D are connected by a wire. So A and D are the exact same electrical node, no difference. Okay. As long as it's connected by a wire, it's the exact same node. So far, so good. Okay, so the 40 ohm resistor is the other end of the 40 ohm is going to E or B. And so I can simply draw a line that extends all the way there. So I'm done with this branch. Cancel it out. Okay. Let's go back to that question. Yeah, only between A and B. That's it. That's the only question. So, all right, so 40 ohms is done. Now, the other resistor connected is 30 ohms. So I want to start with 30 ohms. I'll go a little bit away from the 40 ohm resistor. And this is the 30 ohm resistor. Now, the other end of 30 ohms is C. So I'm going to note this as node C, just to keep track. Okay. And again, the objective is to get or to reach node B. So if I follow node C, what is connected at node C? We have a 20 ohm resistor and we have a 4 ohm resistor. So let's draw out the 20 ohms. And then I also have a 4 ohm resistor. Erase and do this. And that 4 ohm resistor is going to be an E. So far, so good. So I'm done with the 4 ohm resistor. I'm going to cancel that out. Not yet done with the 20 ohm. What is connected at the other end of the 20 ohm resistor? Or where is it connected? A. Absolutely. It's connected to A. So I'm going to draw a line. I'm going to go here. It's connected to A. So at this point, I don't want to analyze the circuit yet. I just want to keep drawing. Okay, I just want to keep drawing. So it's connected to A, 20 ohms is done. My 30 ohms is also done. The only remaining resistor is 60 ohms. 60 ohms goes from D to E. Where is D? D is right here at A. So that's 60 ohms, also done. Then I can check and verify for myself. I counted 5 resistors in the original circuit, and I've redrawn the circuit, and I still have my 5 resistors, meaning all resistors are accounted for. Now all resistors are vertical. Now I can begin analysis of the circuit. The easiest thing I can see to reduce is the 40 ohm and the 60 ohm resistors. They are both in parallel, right? They're both in parallel. Then, since I've solved this before, I know how it goes. But let's say I'm solving this for the first time. This still doesn't quite make sense to me. So I'm going to redraw the circuit again. This time I know how much space I need. I'm just going to actually, let me just draw it like right below. A and B. Let's get these out of the way first. That's the 4040. That's the 6060 in parallel. Then I have 4 ohm resistor. Actually, I'll worry about 4 ohms later. But I have the 30 ohm resistor. And I have the 20 ohm. The 20 ohm is also connected to A. So I'm going to draw it out like this. So this is my 20 ohm. Now, where is the 20 ohm connected? The 20 ohm is connected to the other end of 30. So I'll make that connection right here. This, of course, is node C. And from node C, I have 4 ohm resistor coming down. And that's it. That's the end. Well, end of my redrawing. My advice to students is always to redraw the circuit as many times as you need until it starts to make sense. Okay. This is what I did when I was a student, and I still use it to this day. I have the mentality, I'll keep redrawing the circuit as many times until it starts making sense to me. So you might need to redraw it 2, 3, 4, 5 times. Cancel out, redraw as many times as I need. And now it's quite obvious. My brain can grasp, can look at it and see that 20 and 30 are in parallel. And once we reduce those parallel resistors, what is the relationship between that and the 4 ohm resistor? They would be in series. And then once you reduce that to one single resistance, all 3 of them are in parallel. That is my REQ between A and B. And that's it. That is the answer. Or that's the process. So let's take a pause, think over that. Let me know if you have any questions about this technique. Any questions? How much time do we have left? We're almost there. So resistors in series and parallel. It's 3 problems. Again, they're rather straightforward. 2 of the problems are similar to this. It's like a diamond-shaped circuit. And then when we get to series parallel equivalent analysis, meaning we use these techniques to reduce it down to one single resistance and then expand the circuit back up again to apply Ohm's law, meaning there is a source in the circuit. Could be a voltage source or could be a current source. There is a problem that looks similar to this. It's a diamond-shaped circuit. All we have to do, yes. Okay, so the question is, how do I know whether A, D, E, and B are related? Right? Okay, so the problem simply gives us this diagram, and it asks us to find REQ between the terminals A and B. And then once we observe the circuit from the observation, we can look, and this is simply by observation, that A and D are connected by this wire. So they are simply marked as A and D, but there is only a wire between the 2 terminals. And because there is a wire, A and D are exactly the same node. And so that's one of the reasons I specifically chose this problem, because it reinforces the concept that if you have a wire between 2 nodes, they're electrically the exact same node. It gets, sometimes it does get tricky when, especially when we learn circuits for the first time, or if you have not touched upon circuits for a long time. We look at a diagram and then there's different nodes and the different nodes are separate. But the concept that I want students to retain is that if there is a wire between 2 nodes, then it is the exact same node. It could be a dot, it could be a small line, it could be a really long line. So here we have kind of like a small line between A and D. And that line indicates it's a wire. And that wire means it's the exact same node. Does that answer the question? And the same thing with B and E. There is a wire between B and E. And so if there's a wire between B and E, it is the exact same node. Oh, you're asking why did I draw these long lines for A and B? Okay, so because those are the terminals of analysis. The question asks us to find REQ between those terminals. So that's why A. If the question was, and if you wanted to practice finding REQ from different viewpoint, you could choose any other node. Let's say try to determine REQ between C and D, between C and E, for example. So if you want to practice, this is a good circuit diagram. REQ from or between. Let's use between. Between C and D, D and E, or between C and E. So if you want to practice your skills, you can do so by trying to do this. And in that case, the two lines would be C and D, or it would be D and E, or it would be C and E. Okay. So basically, those are the lines that are just representing the measurement terminals for REQ. Okay. Optional exercise. Oh. All right, so hear the bell. It's 10 o'clock. No, it's 11 o'clock. So we'll end class here today, and we'll pick up here on Monday. Monday is quiz 1. Read through the quiz schedule page if you have not. All the quizzes are on there, specifically what we are going to do every single week. Okay. And so quiz 1 is already on there, probably be around 20 minutes in length from 10:10 to 10:30, and then 5 minutes after that to submit. There's no online option for quizzes. Everybody must be present in the classroom. All right. So have a good weekend, and I will see you all on Monday.